Good morning and welcome back to this postgraduate video course on advanced hydrology. In the last class, we looked at the discrete convolution equation, definition of unit hydrograph, then the assumptions and limitations that are involved with the theory of unit hydrograph. Then we looked at the calculation or derivation of a unit hydrograph, and we looked at the case 1, which was for the simple storm or an isolated single storm. Then we started looking at the derivation of a unit hydrograph given a complex storm, all right, or the rainfall and flow data corresponding to a rainfall event in which there is more than one rainfall impulse of duration d. Okay. And then we said that we can use the discrete convolution equation in the reverse direction, all right, which is called the deconvolution process to calculate the unit hydrograph, all right. So, we will come back to that problem and start looking at this derivation of unit hydrograph in a complex storm. So, you see here we are at case 2, which is the complex storm of durations of multiples of d. Let us say this is the effective rainfall heatograph in which you have more than one effective rainfall impulse of duration d, all right. And then we define various terms. Then we define these various terms. For example, this P m is the axis rainfall depth with m going from 1 to capital M, Q n was the direct runoff hydrograph ordinates small n going from 1 to 3 all the way up to capital N, all right. And then let us say U is the unit hydrograph ordinate which we need to find out, all right. Okay. Then we said that we are going to use this discrete convolution equation which is given by equation number 7.4.1. all right. And then we said that the number of unit hydrograph ordinates which we need to find are this, that is n minus m plus 1. Okay. So, we will get started with this. The first step is to expand this equation 7.4.1, all right. If we did that, and we will do that for what n values going from 1 to 3 all the way to what capital N, all right. So, we will have n number of equations. So, we will write this q n for small n varying from 1 to capital N, all right. So, we have seen this earlier in the last chapter actually when we looked at this time area diagram, all right. So, what I will do is I will not spend too much time on that, and I will write these equations directly, all right, and then go to the two methods which we can use for the derivation of the UH, all right. So, let us look at this now. So, you will have q 1 is equal to P 1 u 1, q 2 is P 1 u 2 plus P 2 u 1, q 3 will be equal to what P 1 u 3 plus P 2 u 2 plus P 3 u 1, all right. And then we keep on doing this, all right, and we go to let us say q capital M, all right, will be what P 1 u capital M, all right, plus you can keep on doing that all the way up to P m and u 1, all right. And then the next one would be what q m plus 1 would be P 1 u m plus 1 plus P 2 u m, and then all the way to your P m of u 2, all right. And the next quantity would be your P m plus 1, which is actually not there. So, that will be 0, all right, and then so on. Okay. So, what I am going to do is from here I will go here, okay, and then write the equation for let us say q n minus 1, right. I am giving you all the equations so that you can expand this for any value of n and m. Okay. It will be P m minus 1 u n minus m plus 1 plus P m u n minus m, and then rest of the terms will be 0, all right, because P m plus 1 is not defined, all right, or P m plus 1 does not exist, because there is only m plus 1 there is only m number of rainfall impulses. Okay. And in the last ordinate of your direct runoff hydrograph, it will be P m u n minus m plus 1. Okay. There is going to be only one expression in the summation, all right. So, this way we see that we can expand this discrete convolution equation to get us n different equations, all right. So, you have n equations. What are the unknowns in this equation? The unknowns are the unit hydrograph ordinates. These q's are known to us, that is the direct runoff hydrograph ordinates. We have this data, all right, that is given to us. We also know the effective rainfall data, all right, and our objective right now is to find out the u's through a deconvolution process, all right. So, you have n equations, or let me write it. This is a system of equations in which a total of n equations are there, all right. Givens are what? Your q's and p's, and we have to find or determine the u's. Okay. All right. So, let us move on and then see that we are going to say that this can be done by or it can be done in many ways, in fact, that is determination of the unit hydrograph ordinates given the rainfall and direct runoff hydrograph data, all right. But we are going to look at two methods, and the first one of them is called the method of successive substitution, all right. So, let us look at that. Method of successive substitution. All right. The above capital N number of equations which are given to us, equations can be used successively. What do we mean by successively? One after the other, okay, for estimating the u's starting from, for example, the first equation, all right. What is the first equation? If you go back, the first equation is this one, all right, which says q1 is equal to p1 u1. What are the knowns? What are the unknowns in this? Well, q1 and p1 is known, only thing unknown is u1. So, can we calculate the value of u1, that is the first unit hydrograph ordinate? Sure, okay, it is very simple. u1 is going to be equal to what? q1 over p1, all right. So, that is very simple, all right. And then, so you have the value of u1, what do we do? Then substituting this value of u1 in the second equation, all right, to get what? u2. Let us go back. Okay. You look at second equation, that is this one, the one I am underlining with the pink color. q2 is known, p1 is known, u2 is what we want to find out, p2 is the rainfall which is known, and u1 is something we just calculated, right. So, only thing unknown in this equation is what? u2, which we can find easily, all right, from this equation, all right. And then what we do is we keep on marching ahead using these equations. Next equation we can calculate u3, next equation we can calculate u4, and so on. up and until we can calculate or we are able to calculate all the ordinates of the unit hydrograph. All right. So, this is what is called the method of successive substitution, in which you just start from the top. All right. Calculate one ordinate, calculate the next ordinate, and so on of your unit hydrograph. Okay. So, this is a very simple method. However, there are problems with this. Can anybody think of some problems? Well, it says that you start from the top, right? What if somebody starts from the bottom? All right. For example, you look at this equation. In this equation, only thing unknown is what? This guy here, the last ordinate of your unit hydrograph, u n minus m plus 1. All right. Q is known, P is known. All right. So, what we can do is actually we can go from the bottom, all right, go up, use n minus m plus 1 number of equations, and then come up with a different set of unit hydrograph ordinates or a different solution. All right. So, you start from the top, you will have one unit hydrograph, you start from the bottom, you will have another unit hydrograph, and somebody else may pick up any number of n minus m plus 1 equations, all right, from the middle. All right. So, you will get another set of solution. All right. So, you do not get a unique solution using this method. All right. Why is that? Well, let us look at this. The number of equations available are how many? As we just said, there are n equations, right? How many number of unknowns are there? What are the number of unit hydrograph ordinates? Well, that is n minus m plus 1. Okay. That means you have more number of equations than the unknowns. All right. So, you have a system of linear system of equations, which is what is called overdetermined. Right. What is an overdetermined system? When you have more number of equations than unknown. If you have number of unknowns and then you have number of equations same, then it is very easy to solve, you will get a unique solution. But when the number of equations are more, your system is overdetermined, and then depending upon which n minus m plus 1 equation you would use, you will get a different solution. So, there is no uniqueness to the solution. All right. So, the system of equations is overdetermined. Okay. The solution is not unique. As a result of that, you will get different solution. All right. Therefore, one needs a solution methodology that uses all the data or all the equations. Okay. So, what is happening is actually we are using less number of data. Total number of data that is available to us in terms of DRH ordinates is capital N, right, n number of ordinates are there, but we are using only part of that. That is why you are getting a wrong solution and which is not unique. Okay. All right. So, now what we will do is we will look at a second method, which is called the method of successive approximation. All right. This is again it is a modified version in which you will carry out the iterative procedure. All right. And this is a method which uses all the data or all the ordinates. All right. It is an interesting one. So, what I will do is first we will look at the step by step procedure and then we see if there is any problems. The second method is called the method of successive approximation. And this is proposed by Collins in 1939. All right. So, remember what we have is this: you have this complex storm data, all right, and then from there you have a single DRH, all right, and our objective is to find the unit hydrograph ordinates, all right. Okay. So, let us look at the step by step procedure of this. First thing you do is you say let the given DRH B is equal to, we will say DRH 1. Okay. We will do a series of computations in which we will redefine your DRH. So, let us say the DRH that is given is, we have redefined that as DRH 1, the first one. Okay. Then we assume a unit hydrograph. Okay. What do we mean by a unit hydrograph? We assume some ordinates of the unit hydrograph, all right. It can be arbitrary, it can be the result of the previous method. We can use the method of successive substitution and get the initial guess or the initial ordinates, all right. So, let us say we assume some unit hydrograph and apply it, means the unit hydrograph, to all excess rainfall blocks, all right, of the heatograph, okay, except the largest one. And calculate the runoff response, and let us call that DRH 2. Okay. So, what we are doing is, we are saying that the given DRH is DRH 1, all right, and then we calculate the direct runoff hydrograph response, all right, from the catchment from a effective rainfall heatograph, all right, the whole except the largest one, all right. So, if you look here in this one, which is the largest one? This one. Okay. So, what you do is you calculate the DRH from all the effective rainfalls, this one, this one, this one and this one except this one, all right. You calculate the DRH and let us call that DRH 2, all right. The next step, you compute DRH 3 as DRH 1 minus DRH 2. Okay. So, what we have done is we have subtracted. So, subtracted means basically what we are trying to do is we are using the principle of superposition here, or you are doing the process DRH 1 minus DRH 2, all right. So, DRH 2 is what we have found out. So, you are subtracting that from the original DRH to calculate DRH 3, all right. What will that be? This is, which is your DRH 3 is what? Is the DRH due to the largest ER block. Is this clear? If you look at this figure here, the original DRH is due to the whole input, all right. The second one is due to all these effective rainfalls except the largest one, all right. So, if you subtract the two responses from the method of superposition, what you will get is the result due to this largest one, all right. That is what we are saying, all right. Then what do you do? Then you divide the DRH 3 which you have just obtained ordinates by what? By the max ER block, that is this one, Okay. If you do that, what will it give you? You have a DRH resulting from certain amount of rainfall, largest effective rainfall block. So, you divide that DRH by that amount of rainfall, what should you get? Well, unit hydrograph for that duration, isn't it, by the principle of proportionality, right. Okay. So, you divide the DRH3 ordinates by the maximum ER block, all right, to get the ordinates of the UH of d hour duration, okay, and that is resulting from the largest ER block. Okay. Let us call that some UH2, all right, and initially we had assumed some UH, all right, this one, and let us say that this is UH1. Okay. Then in the next step, what you do is you compute the weighted average or average, all right, of what? The assumed UH, UH1 and the residual UH which you have just found out in the previous step, let us say UH2. So, what we do is we take some kind of average, right, either the weighted average or the simple average, or in some form we find out the combined effect of these two unit hydrographs, all right. Okay. And use the result for next step. Okay. What is the next step? Well, number 4 is repeat the previous 3 steps. Okay. So, all you do is repeat this previous 3 steps until the residual UH. What is the residual UH? Well, it is UH2 which you are refining at each iteration, does not differ by more than a permissible amount. Okay. So, what we are saying basically is that we keep on iterating, all right. We assume some certain unit hydrograph, we calculate the DRH due to the largest ER block, all right, divide by the largest ER to get the revised estimate of UH, do some weighted average, do the whole process again and keep on doing it until some level of acceptable error is reached in terms of the unit hydrograph ordinates or the total volume or whatever criteria. All right. So, that way we can find the final unit hydrograph which uses all the data. All right. So, this method is much more accurate than the first one. All right. However, these two methods or this method even has some problems. Okay. So, what are those? We are going to look at next. All right. The resulting UH may have some problems. For example, may have erratic variations. All right. What do we mean by that? Erratic variations means the unit hydrograph may look like this, all right. Rather than a smooth curve, it may be the undulations or something like that, or erratic variations, all right. The second one, which is actually not acceptable, is you may get negative UH ordinates, all right. it is possible to get negative UH ordinates, which is actually not acceptable, all right, due to certain numerical and other problems. All right. All right. Some of these can be fixed by smoothing the resulting unit hydrograph. Okay. Right. What we are going to do next is we will look at couple of more methods which are more sophisticated than these two, right, and which are more robust and take care of some of these problems. All right. So, the next thing we are going to look at is what is called the unit hydrograph by matrix calculations. Okay. Why do we need this? Well, it is needed because of one of these problems. There may be errors in the data, there is non-linearity in the data, all right, there is erratic variations, all right, there is more equations than unknowns, that uniqueness problem, the first one at least, all right, and the last one is the negative UH ordinates, all right. Okay. So, these are some of the problems in the determination of the unit hydrograph for a complex storm, all right. For a single storm, we have seen the procedure which is very straightforward, all right. So, what we do is we will look at the couple of methods, all right. First one is what is called the linear regression, and which will take care of some of these problems, not all of them, and the final one is method by optimization technique, and in this case we will look at only the linear optimization method, all right, and which will take care of actually all of these problems. Okay. All right. So, let us look at the first one, or we say that either the least square fitting or optimization, either of these two can be used, all right, and both of these methods actually are classified for matrix calculations, because it will involve the matrix algebra, and then we can do the inversion of a matrix, inverse of a matrix, and we can calculate the things in a nice manner and compact manner, all right. So, let us look at the matrix form of these equations and how we can formulate these problems, all right. So, we know that the discrete convolution equation in a compact form can be written like this. Do you agree? Let me first number this equation as 7.6.2. What is this equation saying? This equation is saying that the matrix P multiplied by matrix U, U is a column matrix, all right. This is just the column matrix of unknowns, all right. P is a rectangular matrix, all right, and Q is also a column matrix, all right. So, let me say that this is column matrix, this is also a column matrix, and this is a rectangular matrix. So, if you go back to your discrete convolution equation, these ones, all of this set, can you write this set of equations in a matrix form, all right. So, if you look at the right hand side, this is all the equations in which P's are known and U's are unknown. So, you can, this is basically the matrix operation. So, you can have P times U is equal to right hand side, which is the left hand side here, Q1, Q2, Q3, Q4, etc. All of these are known to us, all right. So, we can write this discrete convolution equation like this. Now, the problem is that given what are the knowns? P and Q, that is known to us, right. If that is the case, we want to find out u, all right. There are problems of no unique solution, etc. Okay. If we did that, we have seen that, all right. However, what do we do is, if we say that the given p and u, let us say some assumed u, which was one of the second methods actually we just looked at, all right, some assumed or initial value, all right, then what? Then it is possible to calculate what? I am going to say q hat, or estimated value of the DRH ordinates, such that your P matrix times your U matrix, which is assumed, this is your assumed value, should be equal to what? Q hat, right. So, it will not be equal to exactly the u exactly the q or the DRH ordinates, all right, which is known, but it will be some other values q hat, and then if you find the difference between q hat and q, that will be the error, all right. So, what we are doing is that initially we start with some assumed value of u, calculate the computed value of q, calculate the error by finding out the difference, all right, and then we try to minimize that error. So, it kind of becomes an optimization problem, all right. So, then we define the error matrix, your E, as what? As your true values of q minus the computed values of q, all right. This is your error matrix. And then what is the perfect solution? Well, the perfect solution is obtained when your error matrix has all the zeros. Okay. So, obviously, it will be very difficult to achieve that, but we try to minimize the entries in your error matrix, all right. So, let us look at the least square method first, okay, which is also called the and I am going to number this as the number 3, because we have already seen the two methods. We will say solution by linear regression. Okay. Actually, it is also known as least square solution. As you may know that what we do in the linear regression or the regression analysis, it basically uses the least square method to calculate the coefficients or the regression coefficients, right. So, either you say it is a linear regression or the least square method. Okay. All right. So, what we actually do in this particular method is, we first convert the rectangular matrix of rainfalls, which is P, to a square matrix. All right. So, what we are doing actually is, let us say you have this equation P times U is equal to your Q, is not it? That is what we have, all right. So, basically if you see, that would give you U is equal to what? Your P inverse times Q, all right. So, you can directly do that, but P is a rectangular matrix, all right. So, it is not possible to invert a rectangular matrix. So, let us first convert it into a square matrix. Okay. How do you do that? Well, multiply that matrix by the transpose of it. Okay. So, if you did that, we will have P multiplied by the transpose of same matrix times U, okay, is equal to what? Transpose of your P matrix times your q. So, we are multiplying by transpose on the both sides, and let us say that this we call as Z matrix, all right, where your Z is equal to what? P times P transpose, which is a square matrix, right. Okay. So, then that would mean you have your Z times U is equal to P transpose of your Q. That would mean your U is equal to what? You invert the Z matrix, all right, then you already have these things here. Okay. So, this is your solution in terms of U. Okay. So, given the values of P and Q and the Z, which is defined like this, all right, you can find out the U matrix, which is your unit hydrograph ordinates or a column matrix. Okay. Now, this method also has certain limitations. Okay. This method of least squares or linear regression, whatever we have looked at, all right. What are the limitations? There may be, number one, problems in matrix inversion itself, all right. Finding the Z matrix itself can be problematic. Why? Because there may be lots of zeros in it, all right, and not all matrices are invertible. So, there may be some problems related to that. Also, you have or you may have non-negative U's may be produced. It is still possible to have solution of U such that you will have negative values, all right, negative unit hydrograph ordinates, which is again not correct and not acceptable. Okay. What do we do then? We resort to the next method, which is called the linear programming, and that is what we are going to look at next. So, the next method we will look at is called the linear programming. This is an optimization technique or solution by linear programming, and the major advantage of this method is that it allows us to use non-negativity constraints, all right. So, that the solution which you will obtain in terms of the unit hydrograph ordinates or the decision variables will always be positive. Okay. So, in this course actually I will not have time to go through the details or the the intricacies of optimization method itself, all right. I will expect that you understand what is linear programming or the basic concepts of optimization, all right. What we will do is I will look at a step by step procedure which we use in this linear programming, then we will formulate the optimization problem, all right, and will say that the simplex or any other method which is available for the solution of linear programming can be used, all right. So, we will not go too much into the detail, all right, we will just look at the formulation of the problem, okay, so that we are able to get the positive values of the unit hydrograph using this linear programming method, all right. So, what are the steps? If you look here, in any optimization problem or in the linear programming problem in this case, what we do is we need an objective function. An objective function is formulated, all right. What is a objective function in a optimization problem? Well, an objective function can be the cost function which you are trying to minimize, or it can be a benefit function which you are trying to maximize, all right. So, there is a function, all right, which will involve the values of the decision variables, and the decision variables here are what? It is the unit hydrograph ordinates, all right. So, you will formulate some kind of function which you will try to minimize or maximize. So, in this case we will formulate the objective function at the error, all right. So, you have the actual values of q, you have the computed values of q, and the difference of those will be your error matrix, which we have already seen. So, the error function will be the objective function we will minimize, all right. So, this is the first step in which we formulate an objective function, and which in our case will be the error function. Then what we do in the linear programming is we impose the constraints, or we say the constraints are imposed. What do we mean by that? When we say that the constraints are imposed, right, the objective function consists of some formula, let us say some equation which involves the decision variables, right, u1, u2, u3, u4, etc., or for any other linear programming problem it may be x1, x2, x3, x4 and so on, right. Now, when the linear programming solution methodology will search in the feasible region or in the search space, we want to put certain constraint, right, so that the solution which we obtain satisfies certain restrictions or certain constraints, all right. We should not look for the possible solution in the whole domain, all right, because that solution may not be acceptable because it does not follow the certain basic principles or the laws of nature. In this case, the unit hydrographs should be such, or the unit hydrograph ordinates should be such that they obey the discrete convolution equation, all right. So, we will look at the constraints which we will impose in this particular problem. As I said, we will formulate the problem, all right. So, basically the constraints are the one in which we put the limitations on the values of the decision variable, so that they obey those laws or those equations or those constraints, okay. So, that is the constraints. The third step is all possible, which is called feasible in your optimization terminology, solutions are evaluated and compared, okay. So, you are doing you are looking at all the feasible solutions, all right. In the linear programming we are normally on the boundaries, all right. So, we look at all the possible or feasible solutions on the boundaries in the case of linear programming, and we compare various solutions that are available, and then we select the best, all right. So, the last step is optimal solution is selected. Or chosen, all right. What is the optimal solution? Well, the one which gives you the 0 error, okay. So, let us formulate this problem. Let the error E for any equation n be defined as your q n, which is the actual value of your DRH ordinate, minus q hat n, all right. So, that your error matrix, all right, is equal to what? Is nothing but this matrix minus q n hat matrix, okay. Now, let us break this epsilon, all right, this one into two parts. That is positive deviations, which we are calling theta n, and negative deviations, which we will call beta n, all right. Now, there can be three possible cases. Case 1, when your epsilon n is greater than 0, that would mean what? That would mean your theta n is equal to this epsilon, because epsilon is positive and we are saying theta is positive, this one. So, we set eta is equal to theta, and what will be beta for this case? Well, it is the negative component which is 0. So, if your epsilon is positive, then you say that epsilon is your theta and the beta component is 0, all right. We are doing all this so that we are able to impose the non-negativity constraints, all right. Then you have case 2, when you have epsilon n less than 0, that is when the error is negative. Then what? Then you say your positive component is what? Obviously, we say that it is 0, and then you say beta n is equal to what? You want that to be positive. So, you say negative of E n, all right. So, all you are doing is you are just doing some mathematical manipulations, so that your epsilon, all right, you are converting into positive error all the time, all right. If it is positive, you are calling it theta. If it is negative, you are taking one more negative and you are calling that beta, okay. All right. So, we do this, and then the third case is when your epsilon is 0, then what? Well, then theta n is 0, beta n is 0, and we are having a perfect time or the perfect case. Okay. So, with this notations, what I will do is I will give you the formulation of the linear program, all right, in which we will have the objective function and we will have the constraints, all right, and then we can solve that problem using any mathematical software or the simplex method or some other method which are available in MATLAB or Mathematica or any other mathematical software. Okay. What is the objective function? We say that we are going to minimize this sum, which is theta n, the positive errors, plus beta n corresponding to the negative errors, and then n is what? N is an index going from 1 to what? Capital N. This corresponds to all the DRH ordinates, remember that, and this I will say 766. Okay, subjected to certain constraints. What are those constraints? Well, before I go to that, what are those thetas and betas? These are the errors, right. What are these errors? These are coming from this equation on the top, if you see here. Where is the u's in this? Well, u is coming from this guy here, which is the estimated value of q n. So, the constraints we obtain or we impose will be in terms of the discrete convolution equation. The first one is, we say your q n is equal to q n hat, all right, plus theta n minus beta n. Okay. This is your column matrix, this is also column matrix, and these are all your matrix. So, this is your one constraint, which is 7 6 7. Okay. This is nothing but your what is q n? This equation is written for n is equal to what? 1 2 3 all the way to n. So, how many constraints are there? So, there are capital N constraints corresponding to each and every equation, right. So, what you have is then actually let me write one of the equations. So, you will have P n u 1 plus P n minus 1 u 2 plus P your n minus m plus 1 of your u m plus theta n minus beta n corresponding to that is equal to what is your q n. So, this and this is exactly the same, all right. So, we have written it down in the equation form, that is in the matrix form, all right, where n goes from 1 to all the way to capital N. So, what is this constraint doing is that it is ensuring that the unit hydrograph ordinates follow the discrete convolution process, all right. So, the unit hydrograph ordinates which we will get will be such that they will satisfy all these equations, all right. So, we are enforcing these u's to follow the discrete convolution equations, all n of them, all right. So, that we are using all the data, all right. So, it will give you an optimal solution. So, that is one constraint. The second constraint we impose is that this unit hydrograph ordinates which we find should be such that the area under the unit hydrograph should be equivalent to 1 centimeter of effective rainfall, or the direct runoff depth should be equal to what unity, all right. So, we ensure that, and the next constraint then we say is that the summation of u m's, all right, should be equal to k. Okay. I am not going to go into the detail of this too much and then say that this is 7 6 8, no, this is 7 6 9. In fact, this equation was 7 6 8 and this is 7 6 9. Okay. So, what is this equation is doing is this is ensuring that the area under the UH is unity. What is this k by the way then? This k is nothing but the after you convert the units, the area of the catchment in the square kilometers and depth of rainfall and so on. So, this is just taking care of that unit conversion. So, that this is equal to some constant corresponding to area under the unit hydrograph equal to 1, okay, or 1 centimeter of depth. Okay. Then that is it basically, all right. So, and other constraints are always there. So, basically you will say that all the u m's are greater than equal to 0, all the theta n's are greater than equal to 0. These are automatically imposed in any linear programming problem, and then you have betas are also 0. So, this is your complete linear programming problem, all right, linear programming problem LPP. Okay. So, we have formulated this problem, and as I said we can solve it using any of the methods, all right. There is some discussion given in the book at the end of this formulation of the problem, okay, which discusses some of the limitations of this linear programming method, all right. This is also not perfect, no solution methodology is perfect, all right. So, I will request you to kindly go through it yourself, which is given at the end of this particular topic in your Venti Chow's book, all right. So, I think I would like to stop at this point of time because I am at a good stopping point, and in the next lecture we will take up the new topic of synthetic unit hydrograph. What is a synthetic unit hydrograph and how we can actually calculate it or generate it, artificially generate it, and this is useful in the catchments where there is no data in terms of flow or rainfall or anything. Okay. So, we will stop here. Thank you.